Hello again. In this video, I'm going to run through a proof of Theorem 1.7 and illustrate why it works. So you should already know what an R regular graph is. Make sure to read that and understand that definition before watching this video. But once you know what an R regular graph is, what this theorem is claiming, it's an existence of when an R regular graph of order n exists. So R being our degree, our common degree of all vertices, and n being the order of the graph. The claim is that there exists an R regular graph of order n if and only if R is between 0 and n minus 1, and R and n are not both odd. So, and as you watch this video, it might be helpful to read through the proof. I'll sort of reference that as I do that, the proof from the book. So let's start with the proof. Oh, one thing that's going to help us is maybe if you're having a little bit trouble understanding the logic of the proof, I'll highlight a couple things here. There exists an R regular graph of order n. I'll think of this as a statement P, and then if and only if 0 is less than R less than or equal to n minus 1, and R and n are not both odd. I'll think of this as Q. So we're trying to prove a biconditional, an if and only if here. So what we want to show is that P is true if and only if Q is true. Now the first sentence of the theorem says that the conditions are necessary is an immediate consequence of corollary 1.5 and the fact that the degree of any vertex is always between 0 and n minus 1. So what this is establishing, right, it's saying that the condition is necessary, namely this condition, that this is necessary, we should look at corollary 1.5 in order to do that. So what we're proving first here is that P implies Q. That's the first thing that we're proving here. And really what we're doing here, and maybe I'll do it in a little bit more detail, I'm going to prove this by contrapositive. I'm going to prove this by contrapositive. Namely, I'm going to show not Q implies not P. So that is, I'm going to assume that this condition Q is not true. So what this means, not Q implies not P, is that either this condition is true, R is not between 0 and n minus 1, or R and n are both odd. So this is my hypothesis that I'm assuming, and then I want to show that there is not an R regular graph of order n. So that's this first bit. So let's see. So this condition that R is between 0 and n minus 1, this is a given. Yeah, this comes, and they mention this in the proof, right? The degree of any vertex in a graph is always between 0. It's 0 if it's an isolated vertex, and its degree is n minus 1 if it's adjacent to all other vertices. So this is always the case, and so this condition is kind of silly. If R is not between 0 and n minus 1, of course there's not an R regular graph of order n. The degrees just don't make sense. And so this part is proven. That there's not much to show there. This part, on the other hand, takes a little bit of thought, and you should go back to corollary 1.5. When you see something like that in a proof that it follows immediately from a corollary or another theorem, make sure to go back to that theorem and read it again if you don't see it immediately. So what I'll assume here is that R and n are both odd. So what that means, remember, R is my degree of every vertex. So with this one, then degree of V equals R for all V in the vertex set of G. R is odd, and N is odd. So remember back to corollary 1.5, which says that there's always an even number of odd vertices. or an even number of odd degree vertices. And that's what's going on here. It looks like we have an odd number, n, of odd vertices, because every vertex in the graph has order, or has degree r, which is odd. So this is an odd number of odd vertices, which is impossible. So, which is impossible, which means that there doesn't exist this graph, this R regular graph of order n. And so that's proven. We've shown not P. In both of these cases, there does not exist an R regular graph of order n. So now we turn our attention to the converse, that Q implies P. So what we want to do here is we want to assume R is between 0 and n minus 1, and that R and n are not both odd. This is going to give us a couple cases, and we want to show that there exists an R regular graph of order n. Since our goal is to show the existence of something, one thing that we'll do here is we'll just construct a graph with that property. Namely, we'll use the fact that our hypotheses are satisfied and construct this R regular graph of order n. So we'll assume here that R is between 0 and n minus 1. And we have a couple cases to consider. So R and n are not both odd. That means that we could have R and n be both even. We could have R even and n odd, or we could have R odd and n even. So we can really split this into two cases based on R. R is either even or it's odd. And if R is odd, we get to assume that n is even. So I'll break this down by cases. Case 1, R is even. And then case 2 will be R is odd and n is even. So we'll tackle case 1 first, when R is even. So the first thing it knocks out is, right, I want to show this is true for all possible even numbers. The first thing it knocks out is when R is 0. If R equals 0, then what we want to show is that there is a 0 regular graph of order n. So 0 regular meaning every vertex has degree 0, and then so this would be the empty graph. Then the empty graph, so no edges, of order n, is a 0 regular graph of order n. So that means we can throw this case out, and that means we can assume R equals 2k, right? It's even for some k greater than or equal to 1. And by our condition of degrees here, right, n is greater than or equal to, we could say R plus 1. If I rewrite this, right, R less than or equal to n minus 1, same as R plus 1 less than or equal to n. And so we also have that n is greater than or equal to 2k plus 1. And we're going to construct a graph that's R regular of order n. And we do this really by writing all the vertices out in a cycle. So let me try and do that. Let me try and illustrate this. So I'm going to write out our vertices, and this is something we'll do to diagram proofs, is I'll just do a dot, dot, dot. I don't know exactly how many vertices we have, but we have some number of vertices. We know it's at least 2k plus 1. And then I'll call this V1, V2, V3, V4, and so on. This would be Vn, Vn minus 1, and so on. So what we do is we let each vi, for every I between 1 and n, we let vi be adjacent to the k vertices that follow it, as well as the k vertices that precede it in this cycle. So the way the book writes this is that vi is adjacent to vi plus or minus 1, vi plus or minus 2, and so on. So both the one in front of it and the one preceding it, with subscripts expressed modulo n. So what this means is I'll take, say, v1, and I'll make it adjacent to v2, v3, and so on, v4, however many I need, so that this is exactly k vertices here, k vertices. So all k vertices, maybe I'll show it adjacent to this one as well, above that one, and all k vertices preceding that one. So v1 will also be adjacent to vn, vn minus 1, vn minus 2, vn minus 3, and so on, until I get to v n minus k. Sorry, vn minus k plus 1. And I'll do this with every single vertex. Now this will be possible because n is greater than or equal to 2k plus 1, so we'll never run out of vertices. K can't be high enough for us to run out of vertices to make it adjacent to it. And we can just keep going in this manner. So v2 would be adjacent to the next k vertices. It'd be adjacent to v3, v4, v5, v6, and so on until we get to k vertices that it's adjacent to there, as well as the preceding ones. It's already adjacent to v1, but now we need to make it adjacent to vn, vn minus 1, again, and so on until we have k vertices preceding v2. So v1, vn, vn minus 1, vn minus 2, and so on. We'll never run out of vertices to make these adjacent to. We'll do this for every vertex. And what we'll end up with is a 2k regular graph of order n. And that's how this works. Now, the proof, so that's done. That's done with case 1. We've now produced a graph, a 2k regular graph or an R regular graph of order n that has the right, that's what we've done. So that case is taken care of. The next case is when R is odd, but in this case we get to assume n is even. And we'll do a very similar thing. I'm not going to write this all out. You can follow along in the book. We're going to do a very similar thing here, only we're also going to add an extra vertex that's following the vertex. So we'll do all these k, and then we'll add one more that follows this. We won't do the same for the ones preceding it. We'll keep those as just the k. We'll have k plus 1 following v1 and just k preceding v1. And that'll give us 2k plus 1 vertices that every vertex is adjacent to. So that's how that works. And that's how we'll prove case 2 is by constructing that. So I'm going to call this one good. This is more of a proof outline than an actual proof. Again, read through the book. This is only here to help you understand the proof. One thing I'll do here is just kind of illustrate this procedure for both the even and the odd on a couple graphs. V1, V2, what do I want? 4, 5, 6, 7, 8, 9, 10. I think I have 10 vertices here. 3, 4, 5, 6, 7, 8, 9, 10. And let's say our k here is, or let's say our r is 4 here. Let's say r is even. So we're in this first case, we're going to use this method. That means my k would be 2. And what I'll do is at every vertex, I'm going to make it adjacent to the following 2 as well as the preceding 2. So v1 would be adjacent to these 2 and these 2. V2 would be adjacent to V3 and V4, as well as V1 and V10. And I'll just keep going in this way. V3 is adjacent to V4 and V5, as well as the preceding two. V4 is adjacent to those two. V5 is adjacent to those two, as well as the preceding ones. But notice those are already drawn in, so I don't need to draw them again, nor should I. And there we have a 4 regular graph of order 10 produced with this method that's used in the proof. So what if R is odd? Let's say R is 5. What happens in this case in the proof? So again, I'll draw my vertices. I'll still have, so when R is an odd number, we know n will be even. So V1, V2, V3, V4, V5, V6, V7, V8, V9, and V10 are all of our 10 vertices. So the idea is, right, we'll do the same procedure we did here. Right, so here we're writing R equals 2k plus 1, so our k here would be 2, which means we're going to make it adjacent to the following 2, as well as the previous 2 in this circular order. As well, we're going to make Vi adjacent to, what's the extra one that we add? Vi plus L. So what's our L here? If we look at the proof, L is half the number of vertices. So here our L would be 5, be half the number of vertices. So that means V1 is going to also be adjacent to V6. So we're going to have the same ideas with this one. I'll join up all these vertices, the following 2, the preceding 2, I'll just do this all again. Doesn't take too long to go through this construction. So I have those, but now oh, don't forget V10 and V1. Look at, yep, there we go. Or, oh, maybe I already had that. I did. I already had that edge here. That's that one. So I have all of those in there, but now it's a 4 regular graph of order 10 like I did here. So I'm also going to add in these edges, Vi plus L for every I. And so maybe I'll highlight these. Maybe I'll highlight these in green. We'll also make V1 adjacent to V1 plus 5, V6. So directly across from it when we do this standard position of vertices. So V2 and V7 would also be adjacent, as well V8 and V3, V4 and V9, and V5 and V10 would all be adjacent as well. And so that's how we get the extra edge on every single vertex. Since n is even, we won't leave any vertex out, and every vertex will have this extra edge coming off of it. So that's the idea with Theorem 1.7. Hopefully this helped you understand it a little bit better. But now we have a really nice theorem which tells us exactly when there exists an R regular graph of order n. See you next time.